We spend massive amounts of time writing perfect code to secure our systems, but a flawless lock is useless if bolted to a crumbling foundation. Engineers rely heavily on the concept of a logical sandbox. We assume that a Boolean check, like verifying a password or a digital signature, acts as an absolute binary gatekeeper. If the math checks out, the gate stays shut. Code executes on a physical tech stack, routing electrical signals through silicon and relying on processors guessing future instructions. Forcing rigid logical rules through this physical machinery generates side channels. Heat, timing delays, and electrical fluctuations bleed across the boundaries of our applications. To understand modern exploits, you must look past the code itself and track how attackers bypass software abstractions by targeting the execution environment underneath them. Engineering for security requires an understanding of the machine's physics, ensuring that electrical behavior and clock cycles never override the logical intent of the code. Let's start at the absolute bottom of the stack, the physical hardware. When you power on a modern device, it initiates a sequence called secure boot to prevent unauthorized code from running. An internal boot ROM verifies the first-stage bootloader's signature, which then verifies the kernel, creating a chain of trust. However, debug interfaces left open on production boards allow an attacker to skip the line, bypassing the cryptographic checks entirely. The most powerful of these is JTAG. This hardware interface provides raw, low-level execution control, allowing someone to step through code line by line and read or write memory directly. A secondary hardware interface often left exposed is UART, or Universal Asynchronous Receiver Transmitter. It provides a serial console that can grant administrative access the moment the system wakes up. We saw this physical vulnerability weaponized in 2012 against the Barnes & Noble Nook tablet. Attackers connected to the exposed UART port and interrupted the bootloader. They used a simple memory write command, mw.l, to overwrite the specific memory address handling the signature check with an ARM no operation instruction. By replacing that instruction, the device booted a custom Android kernel without throwing a signature error. The physical execution path was altered before the logic could properly run. Cryptographic mathematics offers zero protection if the attacker holds physical authority over the silicon tasked with verifying them. Even if the hardware engineers properly disable all debug ports, the system remains bound by the physical constraints of the CPU itself. Modern processors use speculative execution. Instead of waiting for a slow memory check, the processor guesses an outcome and executes it ahead of time. This habit of guessing creates a massive vulnerability, known as Spectre Variant 1, or the bounds check bypass. If an attacker tricks the processor into guessing the wrong path at a security boundary, the CPU temporarily executes unauthorized instructions. Once it realizes the mistake, it rolls back the logic, but leaves the unauthorized data sitting in the high-speed CPU cache. Attackers can then time how long it takes to access specific memory blocks. If the access is extremely fast, they know the data was cached, allowing them to leap across trust boundaries. To defend against this, developers rely on compiler-level mitigations, specifically flags like the Microsoft C++ compiler's /Q Spectre. This flag analyzes the code during compilation and inserts specific instructions that act as a strict code execution barrier. It physically stops the processor from speculating past vulnerable branches. Perfect software logic fails if it is compiled blindly onto processors that leak internal state through their own optimization routines. Even at the highest layer, operating systems and web applications, the physical reality of time itself becomes an observable vulnerability. This is documented as CWE208, Observable Timing Discrepancy. It demonstrates how simple comparison functions unwittingly broadcast secure information to anyone watching the clock. We can see the foundation of this flaw in the hardware boot sequence of the Xbox 360. The console verified signatures byte by byte, stopping immediately upon encountering a mismatch to save time. By mapping execution time against correct data, an attacker measures slightly longer comparisons to confirm a correct byte, cracking the signature sequentially. This exact same hardware bootloader concept scales directly up to high-level web server authentication. It's the reason behind OWASP Requirement 2.18, which mandates that web applications prevent username enumeration. If you try to log in with a non-existent account, the server checks the database, finds nothing, and immediately throws an error. But if you provide a valid username with the wrong password, the server takes slightly longer to process the rejection. When servers use computationally heavy password hashing algorithms like bcrypt, that tiny time discrepancy acts as a magnifying glass. The delay becomes large enough that an attacker can observe it over the internet, confirming exactly which usernames exist. Whenever an application prioritizes processing speed over constant time execution, it inevitably turns time into a measurable data leak. Attackers rarely play by the rules of abstract code. They bypass the logic by attacking the physical board, the speculative processor, and the observable clock. Securing a system requires defense-in-depth mitigations across every layer of the architecture. At the hardware level, engineers must sever physical access by disabling boot ROM execution and permanently locking debug ports like JTAG and UART before a device ever leaves the factory. At the microarchitectural level, systems must be rebuilt with specific compiler mitigations to force processors to respect security boundaries, rather than blindly optimizing for speculative speed. And at the application level, web developers must utilize constant time authentication mechanisms. Forcing success and failure states to take the exact same amount of time mathematically blinds timing attacks. Resilient systems treat the physical execution environment as the primary security boundary, requiring that hardware habits and temporal leaks be aggressively contained and understood.